Okay, so our lesson is going to be a little bit different today. We're going to be talking about proofs, which is something that you all haven't seen really anywhere. Geometry is usually the first place that you see proofs. So a proof is a logical argument that shows that a statement is true. It's really just a way for us to organize how we're going to prove or show that an answer is what we think it is. So it almost seems silly at first, kind of the way that you do this, but I'm going to show you some algebra examples and hopefully that'll kind of bring it into perspective. So the most common way for us to do proofs, or the easiest way really, I think, is generally a 2-column proof. There are some other types of proofs that we may talk about throughout the semester, but generally we're going to stick with 2 columns. So what that does is it organizes our way of thinking, and this is a screenshot from another video just because I liked the way that it was set up, but it's set up into 2 ways. So we've got our statements on the left and our reasons on the right. And statements, that's generally like where you kind of show your work. You'll see once we get through an example what I mean by that. And we number them just to keep them organized. And for each statement, we have to give a reason. So we can't just work out a problem because we know it to be true. We have to give a reason for why we're allowed to say what we're saying. And then in the reasons, there are a few different things that we can use for reasons. So we always start with what's given. So the very first reason will always be given. Sometimes those are things that are given in a image. Sometimes they're just statements that are given. That'll kind of make a little bit more sense whenever we get into some examples. And then reasons generally come from 4 different places. They could either be definitions, or properties. So that's why it's really important that we know our definitions so we know how we're allowed to use them for proofs. Or they could be postulates or theorems. So you may want to, well, you need to kind of have this little image drawn out for yourself in your notes. And then we can make a side note about postulates and theorems. So let me zoom in here on this definition. And that is that a theorem is a statement that can be proved. So think like Pythagorean theorem, they had to prove that that was true and worked in all different cases. So that's what a theorem is. And we learned last week that a postulate is something that's accepted without proof. So it's just kind of like common sense, and it's almost so simple that there's not a way to prove it to be true. All right, and then the last little note on here is just logical order. We want to make sure that we say things in order, right? Like you wouldn't give the problem and then like the 5th step and then go back to the 2nd step to show how you did that, right? We're just going to work step by step in order. And again, that'll make sense once we get to a few examples. All right, so there are a few properties that we need to make sure we write down. You have learned these before in algebra, but I just want to make sure that we have them to use. So if I were taking notes, I probably wouldn't, if I'll be honest with you, I probably wouldn't copy down a whole lot for these first properties of equality other than maybe just listing these properties. So addition, subtraction, multiplication, division, all these examples on the right here say is that whatever you do to one side, you have to do to the other to maintain that equality. I would maybe write down the examples for reflexive, symmetric, transitive, and substitution, because it is important that you know the difference between those, particularly later on. So I would go ahead and write those down with some form of the example just for yourself. All right, so we're going to look at one algebra example and one geometry example just for you to kind of get an idea of what this is going to look like. All right, so remember we are going to want to start with drawing out our 2 columns. I don't know why that happened. And on the left, we're going to include our statements. And then on the right, we want to include reasons. So remember, we're always going to start with the given. So the first statement is literally just going to be me copying the problem. I'm not going to change a single thing about it. I'm just going to copy the problem down. And our first reason is going to be given. So I know that seems like a very silly reason. That just means that's what we've started with. So if we were going to solve this problem, I think most of you would say you need to add 4 to both sides. So we don't actually have to show the work that we're doing, but we need to show what the next statement is. So the next statement I'm going to say is 18 equals 3x. And so for my second step, I'm going to say that that is addition. That's what I've used there. And technically, we want to say that that is the addition property of equality. So I'm going to put just addition and an equal sign. All right, and then the next step, I think you all would agree, is we need to divide to get x by itself. So to do that, I'm just going to get 6 equals x. That's what would happen if I divided. So my final statement is going to just be the division property of equality. And then I guess technically if we wanted to say to prove that x equaled 6 instead of 6 equals x, we can use that reflexive property that was on the last slide, and we can say x equals 6. So that would be us just saying reflexive, which I know is like really common sense. It's not something that you necessarily have to do in this algebraic proof, but they'll tell you where you need to end, and if you can end by just saying 6 equals x, or if we need to switch that around to say x equals 6. All right, so that's just a simple algebraic proof. This second example B, we're going to try that one probably at the beginning of class tomorrow together just to make sure we're on the right track. All right, so let's look at an example of a geometry proof. So just like we said before, we're going to start with the given, and one thing you kind of want to do is just map out a plan in your head of what is going on. So if I look at this problem, I should either be thinking about some postulate that I know, a theorem, or maybe some definitions. And just this picture alone makes me think about segment addition, because I've got two smaller segments, RS and ST, that are creating the larger segment RT. We kind of talked about this last week, but we're just going to put like an official structure to how we set up this problem. All right, so I'm going to start with statements and reasons. So again, we want to start with the given, which is just that RT equals 5x minus 12. We're going to use that. It'll be a minute before we kind of put that in our problem. So we're going to say that that's given. So we just said that this was segment addition. So the second statement I'm going to say is that RS plus ST is going to equal RT. And the reason I know that that's true is this is an example of segment addition. All right, and now what I want to do is go ahead and maybe substitute some of those values. So I guess there's actually something else that we need to add to this original given statement. So I'm going to say this statement right here, and then I'm also going to say, I'm kind of doing a cop-out here. I'm going to write picture, because the image itself is given, so we are allowed to use the information from the image to work out this problem. All right, so step 3 rather, is we need to maybe start solving some of the algebra. So we know that RS is x plus 2, and ST is 3x minus 8, and RT, we've already said, is 5x minus 12. All right, so the reason I can do that, we just said, was substitution. Because if you think, I've taken the geometry statement that I made in step 2 and I've replaced it with algebra parts. All right, now we're just doing some basic algebra skills. So step 4, we might say combining like terms, which is also, I guess, technically substitution, but we can use some of this algebra terminology for right now. So I'm just going to simplify that and say 4x minus 6 equals 5x minus 12. And now we're just, again, doing some of our algebra properties. So if I combine our x's, all right, we can make that say negative 6 equals x minus 12. I did that using subtraction. And that was subtraction of equality. All right, and then step 6, I can use addition, so I can move the 12 to the other side, so that's going to be 6 equals x. So that's going to be addition property of equality. And then step 7, remember, so this one was a little different. They've actually told us what they want us to prove, and that is that x equals 6. So we've got to flip this around just like we did in the last one to make x equals 6. And remember that other property, that was symmetry that allowed us to do that. And that was the symmetry property of equality. All right, so this is kind of the structure that we're looking at. Not all of them will be this long. Some proofs we do will be very short, but I just want you to kind of get a general idea of this structure. So this is a lot of what we're going to be spending some time on tomorrow.